In section 9.5, we take a look at directional derivatives. Consider that we've already have looked at contour graphs. That was when we had something that was in 3 dimensions, and we plotted that in a 2-dimensional frame by considering these level curves. So if you are living on Earth, Earth has different elevations, but when you look at a map, the map is drawn out in a flat 2-dimensional page. So on this map, you can have these lines here, these level curves, and this particular level curve here tells you that for all of these points on the map here, their height is 80. This could be an elevation of 80 miles above sea level, right? So this 2-dimensional representation, it can give you some information about the 3-dimensional elevation of Earth through these level curves and these numbers. So if the elevation was a function of x and y, where x is the horizontal scale and y is the vertical scale, you can talk about partial derivatives here. So at this particular point on the graph, if you were considering the partial derivative of f with respect to x, you're asking if you would go up on the x value, what would happen to your height, the elevation of your function f of x, y. At this initial point here, we have an elevation of 10. And as you head over towards the right-hand side, you will be headed over to an elevation of 80. So your elevation would be increasing, and that will let you know that your partial derivative of f with respect to x is some positive number. On the flip side, if you go up in this direction, where your y values will be going upwards, you would be starting from an elevation of 70 and headed towards an elevation of 60. So your elevation would have gone downwards, and therefore the partial derivative of f with respect to x, with respect to y, would be a negative number. But when you're walking the globe, you're not limited to only walking left or right or up or down. You can actually travel in all sorts of different directions. And this concept is what directional derivatives are trying to capture. Consider looking at the function f of x, y is equal to 0.3x squared plus 0.3 y squared. So just a simple paraboloid. In 3 dimensions, again, we'll have the positive x-axis coming out towards you, the positive y-axis going to the right, the positive z-axis going upwards. If you were at the point 1, 1 right there, and you were standing on this graph, depending on which direction you walk out, you would have a different experience. If you walked out in this direction, you would be going upwards. If you walked out in that direction, you would be going downwards into that valley. If you're walking in the direction of the positive x-axis, in this direction, your path will look something like this on that graph. And if I orient this in just the right way and delete the graph, this is what the path will look like for you. So if you walk out in that direction, you would be going upwards. So if you're talking about the elevation, the partial derivative of f, your elevation, with respect to x would be positive, because if you go out in this direction, your elevation would increase. If you were, let me orient this in just the right way. If you walked out in the direction of the positive y values, that way, the path you would be walking would be this path. So as you're going in this direction, you would be going upwards. So the partial derivative of your f with respect to y would be a positive number. But let's say you were going in the direction that carried you downwards towards the bottom of that graph. Then your graph, your path, will look something like this. Sorry. I clicked the wrong button here. Let me orient this in just the right way again. Oh, I changed the values of A and B. Let me change it back to 1. Okay, there we go. All right, so if you were going along that path, as you traverse that path, you would be going downwards towards the bottom of that graph. So your partial derivative with respect to this direction would be negative.